Let's look into another very useful characterization of continuity. So in this case, for X and Y metric spaces, the mapping from X to Y is continuous on X if and only if the inverse image of every open set V in Y is open in X. Okay, so what we are doing here, we have our X and Y and our mapping F. What we are saying is that given any V that is open in Y, its inverse image is an open set in X. Then that is equivalent to continuity. Just a quick reminder, the inverse image of a set, this is from chapter 2, is by definition the set of points in the origin space such that f of x belongs to V. Okay, this is just as a reminder. Okay, so proof. Here we have an equivalence, so we have to prove both directions. So let's start from left to right. Let's assume f continues, and then we need to prove the right-hand side. Okay, so to prove the right-hand side, because we are going to prove that the inverse image of V is open, for every open set, we need to take some open sets. So assume F is continuous and V subset of Y is open. Okay, so we want to show that F minus Y of V is open in X. And remember, the definition of open means that there is a ball contained. Okay, what we are going to try to show is that these sets contain open balls. All right, so the only thing we have is the definition of continuity. So we need to use that. So let's do another picture. So this is our V, okay? And we are going to take some point P in V, sorry, not P, because this is in the image. Let's call it F of P, okay? And it comes from some point P that is contained in X. Okay, and this is our Y. Now, because V is open, that means that there exists some epsilon such that I can take an open ball around F of P that is completely contained in V. Okay, so that means that the distance between F of P and Y is less than epsilon for some Y's in V. Okay, so let's write it like this. There exists epsilon bigger than 0 such that if the distance between F of P and Y is less than epsilon, then Y is in V. Okay, this is equivalent to saying that the ball of radius epsilon around F of P is contained in V. Okay, it's the two ways of saying the same. Now, because F is continuous, Okay, for the same epsilon, that means given epsilon, there exists some delta that depends on epsilon, such that if the distance between x and p is less than delta, then the distance between f of x and f of p is less than epsilon. And these are the distances in x and y. So going back to our picture, that means that we can find some small ball of radius delta around P, and we can be certain that for any point, let's use a different color, for any point x that is in that ball, it's going to be mapped by f to some point f of x that is in the ball of radius epsilon around f of p. That is by continuity. Okay, but now here notice what is happening. The distance of x, when we have this distance here, what we are saying is that there is a ball of radius delta around P that is completely contained in the inverse image of B. Okay, so that means, by definition, that the inverse image of B is open as we wanted. Okay, I could even write here x belongs to the ball of radius delta. All right, so that completes one direction. We need to prove the other direction. In this case, what we are going to suppose is that f, the inverse image of V, is open in X for every V in Y that is an open set. Okay, and here we want to show that F is continuous. Here we need to use the definition of continuity. Okay, so here the tool we have is that we can choose any open set. So what we are going to do is to choose a set that goes in our favor. So we are going to, it's similar to before, so let me repeat the sketch. Of course, these pictures have no substance, but they help to understand what we are doing. So what we are going to do, we are going to take some P here, and we are going to look at f of P, and we are going to define V as the ball of radius epsilon around f of P. Or in other words, V is going to be the set of y's in capital Y such that the distance from y to f of P is less than epsilon. This is the distance in the metric space Y. Okay. So this is an open ball, so it's clearly an open set. And what we know by hypothesis is that f minus 1 of V is open. Okay. And that means that there is a neighborhood around P that is completely contained in the inverse image of V by F. But then by definition of neighborhood, open neighborhood, here what we have is the distance between X and P less than delta. Okay. So in this neighborhood, if we have X that is in this ball of radius delta around P, then the way we have defined things, we know that f of x must belong to a ball of radius epsilon around f of p. Okay? So that means, looking at the definitions, the distance between x and p is less than delta. The distance in y between y and f of p is less than epsilon. But now let's be careful, because it's not any y, it's the precise f of x. And here what we have is, remember the beginning of the proof, that for every epsilon there exists some delta, right, such that if the distance between x and p is less than delta, then the distance between f of x and f of p is less than epsilon, and we have our continuity. And that completes the proof. There is a very useful corollary. This can be useful for the exercises, that says that if we have a mapping from x to y, xy metric spaces as usual. Okay. So f is continuous if and only if the inverse image of a closed set is closed. So inverse image of C is closed for every C closed in Y. Okay, so of course the inverse image is closed in X. Okay, and here the proof is actually very simple, because it follows from the previous theorem, right? We just need to use the complement, well, the complement of a closed, the complement of a closed set is open. Okay, so here we are basically saying the inverse image of the complement of E is the complement of the inverse image. Okay, and putting the two things together, we get the proof. I leave this as an exercise. You can do it by yourself. One final comment. This is actually very straightforward, but I just want to mention it. When we have complex functions, and they are continuous, okay, let's say both of them go from a metric space x to y. So what we have is that the sum, the product, and the quotient, this for non-zero, as long as the function is not zero, those are all continuous. This is also something that can be proved using the definition. I leave it as an exercise.